So we've defined now what it means for two sets to have the same number of elements, whatever number of elements means. So it's weird, right? We haven't not defined what is the number of elements of a set. We've only defined what it means for two sets to have the same number of elements. But what if I want to say like a set has 3 elements or 4 elements? What does that mean? Can we define that? Well, the way we've constructed the natural numbers gives us a nice advantage here. So this didn't have to be. Like if we had constructed the natural numbers in a different way than what we did, we wouldn't end up with the following awesome feature. If you look at 0, it was set up to be a set that has 0 elements. In fact, you will find the set that has 0 elements. If you look at 1, then the definition is its next 0, right? The successor of 0. So 0 union singleton 0. But each time you're doing something union singleton itself, you're just, if I just write the something here, you're just taking what it originally was and then throwing its own self into that list, right? So like maybe it's clearer when you're looking at the next one. Literally the next one. Next one is 1, which is singleton 0, unioned with singleton 1, right? So 1 union singleton 1. And what we're doing is taking the previous list and then throwing the entire list itself into that list as a new item, and then creating a new list. Then what's 3? It's the next of 2. So that's 2, which let me write it like this, union singleton 2. So that's like taking the previous list, basically, and then throwing in one new item, which is the entire previous list. But I'd rather write that as 2, which is a short name for that list. So look, 0 is a set that whatever having 0 elements should mean, I think 0 has 0 elements. 3, whatever it should mean for a set to have 3 elements, I do think 3 is an example of a set that has 3 elements. So even before having defined the notion of having 3 elements, it looks like I've set things up so that each natural number n, I think, has n elements. That did not have to be, so let me emphasize that that is an artifact of the way we have constructed the natural numbers here, which comes out of the way we defined succession. Our successor operation works like this, and that achieved that magical property that we're looking at, where each natural number has the itself number of elements. 2 has 2 elements, 3 has 3 elements. But we did not have to define successor this way. Other people might define succession a different way, and as long as they end up with the same, as long as however they define succession, however they define order, they end up with the same theorem 96 here, and also, I guess, the same this. As long as these parts are the same, they're going to end up with the same theory of natural numbers. And their version of natural numbers would be just as good as our version. So what we're doing here is exploiting an artifact of our particular construction. But why not exploit it? It's available. Sorry to keep repeating myself, but just to summarize that point again, if you go talk to someone else who may have also constructed the natural numbers, perhaps also using set theory, but did it in a different way than us, then they might disagree with you about the elements of 3. If you tell them 3 is a set that has 3 elements in it, they might disagree with you about that, because in their construction that might not be true. That's an artifact of our particular construction, and we're taking advantage of it shamelessly. So here is where we take advantage of it. We're going to define this. A has n elements if and only if n is a natural number and A has the same number of elements as n. So if someone says A has 3 elements, this phrase here, this proposition, then we have defined this predicate altogether, has 3 elements. What that means is that 3 is a natural number, which we already knew, and it means that A has the same number of elements as 3. So there exists a bijection between A and 3, which, by the way, is this set. That set is 3. So it is an interesting artifact or feature of our particular construction of the natural numbers that each natural number is the set of the natural numbers less than it. So this turns out to be a very good way to define the concept of having 3 elements. Next, we say a set is finite if and only if there is some natural number, there exists some natural number such that it has that many elements. So what we're defining here is this predicate is finite. So this proposition, A is finite, is true if and only if there exists n, such that n is a natural number, and A has n elements. And let me spell it out completely what it means to say A has n elements, just so you can see our full definition of finiteness in all its glory. A has n elements means, well, first of all, it means this, right? And n is a natural number. Okay, so I don't need to say n is a natural number twice. So just this, right? But what that means is there exists a bijection. There exists f a to n such that f is bijective. And there is our definition of finite. In fact, you can always it's totally harmless to pull this existential quantifier out to there. So we can write it like this. So there exists a natural number and a function from A to that natural number, which is bijective. So a finiteness claim is an existence claim. It's a claim that there exists a function and a bijection. Is a natural number and a bijection. And then finally, infiniteness. What does it mean to say a set is infinite? Is to say it's not finite. So it's just putting a negation on the is finite definition. Now if you look at the is finite definition, that's 2 existential quantifiers, right? Exists n, exists f, such that blah, 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 blah. So what would an infiniteness statement look like? If you push the negation in, it's actually a universal quantifier, right? So sometimes it's hard to prove. Sometimes those kinds of things are hard to prove. So let's write it out. A is infinite if and only if, well, if and only if not this stuff. That's infinite. So in other words, A is infinite if and only if, for all natural numbers n and functions f from A to n, f is not a bijection. So that's a way to look at it. Now, it would be nice to know this. So this will be a really awesome and actually kind of powerful theorem that there exists an injection from n to m if and only if n is less than or equal to m. And this one too, that there exists a bijection if and only if they're the same natural number. And you'll see there'll be some interesting ways to use these. Now, these take too long to go through, I think, to fit into this lecture. So I will either put it into the next lecture, or maybe I'll end this portion of material here. I don't know, we'll see, but I'm not putting it in this lecture. Instead, maybe what I'll do is do some simpler examples where I use these definitions, where I use these two definitions.